Okay, 3, 2, 1.
Hello, my name is Filippo Pagani. I'm a postdoc at the MRC Biostatistics Unit in Cambridge, and I'm going to tell you about what to do with curved posterior distribution when that you may encounter when you run MCMC algorithms on your models. Why this topic? Because it's not a very well explored topic. There's no general result that can solve all of your problems, so people tend to ignore this, and sometimes it can be fine, but some other times it can create some serious problems for your results. So I feel like it deserves some attention. So this is the outline of the talk. Yeah, I'm just going to start. I'm going to start with like a metaphor. So imagine that your MCMC algorithm is a hammer and your posterior distribution is a nail, right? In this case, in the normal case, the nail is straight, so it's really easy to hit with the hammer properly, and you can use like a reliable heavy hammer that you've always used so far, which could be, for example, the Metropolis Hastings algorithm. Okay, and everything is going to be fine. Unfortunately, though, sometimes the nail is not quite as straight as we would want it. Sometimes it's curved, and in that case, hitting it with the hammer that you usually use is not going to be as effective. So if you're lucky, you can use some transformation. You can, if you're lucky, there is a transformation, relatively simple. This is the first one that comes to mind, that you can apply to the nail to make it more straight. But then in practice, models are complex, so simple transformations of this sort may not fix the problem entirely. Okay, so what are you going to do in that case? If the problem cannot be fixed sufficiently with transformation like this, you can just move on to a more sophisticated MCMC algorithm. And these are just, some examples that came to mind. Great, but then the trouble with MCMC is that you can't see the shape of the nail very well. So sometimes you think you have a very, very strong and powerful MCMC method, which then in practice turns out to be quite disappointing. Okay, so this is why you've got to be careful about curve distributions when you encounter them. Why am I telling you this? Because curve distributions are more common than you think. In epidemiology, they arise in so many fields of knowledge: epidemiology, biostatistics, biophysics, astrophysics, particle physics, finance, economics, and really any field of knowledge. And as far as I understand, they often arise because two or more configurations of the parameter space explain the observed data equally well. An example for epidemiology could be, given the same number of observed sick people, you may either have a large number of sick people that you don't observe, that you don't observe, and then you observe them with a low rate, or you can have a low number of sick people that you don't observe, and then you observe them with a high rate. Both those configurations of the system give you exactly the same number of observed sick people. In that case, usually people get banana-like curved posterior distributions. Another example from astrophysics in this case could be when there's a bright source of photons in the sky, and you're trying to estimate how far it is. It could be something very close but dim, but it could equally well be something very far but very bright. Both the configurations of the state space explain what you're seeing equally well. So in that case as well, you will get some curved posteriors. These are just two examples, okay? And to make it a little bit more concrete, recently, a colleague of mine gave a talk about his new paper, a multinomial a computational approximation basically for a stochastic epidemics model on the Ebola data. And I mean, his work was about decreasing the computational cost without losing accuracy. But then within his work, he used MCMC, and he showed this trace plot. Trace plots usually are the first things thing that people look at when evaluating the convergence of an MCMC method, okay? And to make it a little bit more real, I just thought let's include some real data example to give you an idea of how the workflow goes, and to give you an idea of what I would do if I encountered curve distributions in practice. So this is the trace plots. These are the trace plots from the MCMC run that my colleague did on his multinomial approximation on this epidemics model. And looking at it, usually a plot like this suggests that, at least on this component, the MCMC is doing fine. But then if you look at the other plots, for example, these little bits here are a little bit of a warning flag. Okay, and my colleague was saying that this is probably a second mode that the posterior has in this component, and I can believe that. Multiple modes can be a problem, but it does look like the MCMC algorithm is mixing fine in this case, so I'm not overly worried. On the other hand here, this worries me more, because if it was a separate, it looks like the MCMC trajectory took an excursion, but it's not too far from the main trajectory, sort of. So I don't quite believe it's a separate mode, but otherwise it would go into the mode and out of the mode faster and better rather than being stuck in there like it does here. So this is a warning flag that something weird is going on. These massive excursions here are a big warning sign, in my opinion. And from my perspective, this looks like your algorithm being really constrained in one direction when moving along the posterior, and then suddenly reaching a certain point, that constraint is not there anymore. So the algorithm can take much, much longer steps in that direction. And then whenever the algorithm leaves that spot, it starts being constrained again. So in my mind, this looks like what could be a curve distribution or an L-shaped one, really. So, and the pattern happens because you reach the point where it changes correlation, so you can take much longer steps and then back. And in the end, I got in touch with my colleague. He gave me the MCMC sample, and I plotted the 2D marginals, and this is what came out. So indeed, it does have some L-shaped distributions and some other weird ones, definitely multiple modes as well, like here. And some features, some very weird tails, very long tails. So yeah, it's definitely a very, very interesting looking posterior. But yeah, I was happy to sort of realize that indeed he did have L-shaped or curved shaped distributions from here, his MCMC sample. Okay, so this does happen. This is how you sort of realize that you've got curve distributions from your model. So what are you going to do about them then? Quite a few options. The first thing you can do is nothing. Some people are only interested in the maximum a posteriori estimate, and they don't really care that much about the uncertainty around it, as long as they get the mode right. But in that case, I would say, well, that's fine. In that case, that's fine. But I would say, then why are you doing MCMC in the first place if you don't care about the uncertainty? Right? You might as well do variational Bayes and save a lot of time. So just one thing to think about. So that was number one. The second thing you could do is you could strengthen the prior. Okay, a stronger prior sort of puts more weight on one configuration of the model rather than the other, and gets rid of the curved structure, basically, or it ameliorates it in any way. So that could partly or completely solve your problem, but you've got to be careful, because if you strengthen the prior too much, then no amount of data will ever be enough to change your opinion. And also, it's going to be hard to justify with the reviewers if you do something like that. So maybe be careful. Do a little bit of that, but not too much. One thing you can do, another thing you can do, you can dig up a statistical test to see whether your MCMC algorithm has converged or not. But then which test? There's many. What assumptions is the test relying on? Are those assumptions satisfied on your model? And then if your test says the algorithm hasn't converged, then you've got to do something else anyway. But more worryingly, your test may say, oh, it's all fine, your algorithm has converged, but in the end, it hasn't. And that's a false negative. So that's much more worrying, right? So you've got to be very, very careful. I'm not an expert on the literature on that kind of tests, but I can tell you that I've come across this one, the newer hat for assessing convergence. And in my understanding, this test does two things. It compares multiple chains and the basically difference between their stationary distributions or whatever, and the difference between the resulting MCMC sample that you get from those chains, really. I can imagine things where this can fail. So this is useful, but not probably crucial. What I wanted to tell you about is that this test also measures the quantile effective sample size. And when I was running things on difficult distributions where I knew the truth, I did realize that very often warnings about the tail ESS being too low showed up when I knew that the algorithm wasn't doing a good job. So that is encouraging. So maybe this test is actually worth looking into. I mean, once again, I'm not an expert, but this is included in STAN. And at some point I used STAN, and that's when I noticed that. And some people brought it up in like talks and conversations about these things. So maybe there's something to it. So that is one example of a statistical test to assess convergence, but I'm not an expert once again. So that's just my personal recommendation, if you will. Another thing you can do is, and you should do, in fact, if you can, is use better MCMC algorithms, smarter ones, usually those that are sort of appropriate for your kind of model. Okay, and but then again, which algorithm are you going to use? What quantities do you have available to sort of make available to the algorithm to run, right? So if you do have both the gradient of your target and the Hessian, you could run a simplified manifold Mala, for example, which is a fairly simple algorithm that is quite good at dealing with curve distributions. It's not super simple, but if you're coding in R, I've coded this up already and it's online, so you can just take my code and that's going to make it quite easy. Another good thing is that it doesn't require that much tuning. So once again, it's not that hard to run, and it's a smart algorithm and it works quite well. So there's really no downside to trying it if you do have the gradient and the Hessian available, and you've got to calculate them and code them up. Another algorithm that you could be using is the NUTS algorithm from STAN, which is basically a smarter version of HMC, which decides on its own when to sort of turn around and finish the trajectory. And it's a very good algorithm, and it only needs the gradient to function, but also it does automatic differentiation. So you don't actually have to compute the gradient yourself. You can just write the model and it will find it on its own. And another good thing is that it basically requires no tuning. So, and it comes with automatic tests that give you ideas on how good or bad you're doing. This is all great. The problem is that to run it, you've got to rewrite your model in the STAN programming language, which is probably not super hard, but it's one additional step you have to take. Okay, so there's no free lunch here, basically. There's plenty of other choices of other algorithms that you can use. And if you indeed find some good ones, just let me know. I'd be interested to know that. Another thing you can do, in case you don't have the gradient, in case you don't have the Hessian of your model, you can apply the transport map. What's the transport map? It's basically an algorithm that can work with your original algorithm, and the transport map basically estimates a mapping between a standard Gaussian, which could be your MCMC proposal, and the posterior, which could be curved. And it uses that to propose better moves. And then obviously, you'd be able to explore better the posterior. And the more samples you get, the more you know about the posterior, the more the map will update, and you'll be able to move around better and better and further the more you explore. Transport map is a great idea. Unfortunately, the map is sort of estimated in a way that is reminiscent of polynomial chaos. So you have a lot of terms with, and each of them has a parameter. So as you can imagine, as the dimension of your problem grows, the number of parameters you have to estimate explodes. So it's generally impractical for a high dimensional problem, but for a lower dimensional problem, it's a very, very neat idea. And like I said, it can work with your current algorithm without needing any gradient or any Hessian, even though if you have the gradient, it does help. Anyway, this is just another thing I wanted to mention on the algorithm side of things. It's another thing you can do. And obviously there's code online, and it's already coded up, so it shouldn't be too hard to apply. The last thing I wanted to go through was yet another thing you can do. You can take a toy model where you know the ground truth, and you can shape it, if it's flexible enough, to look like your posterior. And then you can run your algorithm and see how badly or good it does running on that model with a specific shape. It can happen that when you know the true shape of the model, it can happen that what you get from your algorithm is very, very different. And I'll show you some pictures of it later. In that case, then you definitely know that your algorithm is not really good enough for the job. And you should do something about it. I mean, you can do nothing about it, obviously, but you should really do something about it. Benchmark models, right? So like I said, you can take one, shape it as you want, and try your algorithm on which benchmark model. There's many. I'm not going to go into detail, but at some point I was developing a new MCMC algorithm recently, and I needed a curve distribution to test it on. And then I was looking into what benchmark model I had to use, and I couldn't find any that was satisfactory to me, just because they had so many problems. For example, in many cases, the normalization constant was not known, and it's hard to assess how well you're doing if you don't even know the normalization constant of your model. Another problem is that it's hard sometimes to get independent Monte Carlo samples from the model. So often people, what they do is they run a smarter algorithm and they use that as the truth. But what if the model is, very hard, and even the smart algorithm doesn't sample completely appropriately? Like, there are quite a few unknowns there. Often as well, the models are quite rigid in the sense that they're not very, very flexible, and you can't adapt them to take on whatever shape you want, which can be a problem. And I've noticed this, that very often the models are defined in 2 dimensions. And whenever you try to extend them to more than 2 and sort of maintain the features that made you choose that model in the first place, very often they break in different ways. And you see, there are many problems that can arise with benchmark models. And this is why, okay, before that, I'm just going to tell you one, which is quite iconic. This is a Rosnberg distribution, okay? And the plot on the left is what it looks like in 2 dimensions. And if you extend it to 3 dimensions using one of the most popular extensions, the shape of the first 2 variables changes from what you see on the left to what you see on the right. And no one says why. And that puzzled me very much. No one was talking about it, so I couldn't get it out of my head. I had to understand why, and I did. And because of that, I sort of made my own benchmark model, which is basically a good one. This is probably the only equation I'll show you this in this presentation. It's basically about wrapping normal distributions about functions, which in this case it's a parabola, but it doesn't really have to be. And because they are normal distributions and because they are sort of, because the model is built in a certain way, then the normalization constant can be very, very easily calculated. And it's also important how you connect them to each other, each component. So we found that the most sort of interesting way to connect them and to obtain difficult shape was this following graphical model, where we have an original random variable x1, which acts as the dimension number 1, and also it acts as the fulcrum of the whole model, because the model is defined in blocks and every block includes the first variable. And each block is connected to each other, but then each block is connected within the block, but also the blocks are connected between blocks through the connection they have with the first variable, basically. And well, this is the paper where we describe the model which was recently published. And because of this structure, we can obtain very, very challenging shapes like this. This is very, very, very challenging. Why is this a challenging shape in general? I'm going to explain that. Because first of all, it's narrow in this sense. And MCMC algorithms have problems traversing narrow spaces, because if you have a large number of components, every component has to, when you sample a step, every component of the step has to sort of align for you to be able to go in a single direction. And if you've got to traverse a long, narrow ridge, then that has to happen multiple times, which is very, very unlikely, especially for a random walk. And this is why ridges are complicated to traverse for MCMC algorithm of the easy kind. In general, that's not a problem, because if the ridge is straight, you can just apply a rotation and rescaling matrix to your transition kernel from your MCMC, which is fine. But in this case, the shape is curved, so you cannot do that. You would need like an infinite amount of linear transformations to apply to your proposal to be able to use that technique to move around the shape like this easily. Obviously, you can't. And that's why people came up with transport map, because the transport map is essentially equivalent to having an infinite number of linear transformations to adapt your proposal to your target distribution. So this distribution is particularly hard to sample from, the one you see, which is just an example of the hybrid model with hybrid Rosnberg with certain parameters and a certain block structure. This is hard to sample from because it's narrow, it's curved, and it has, if you look at the scales here, the scales, this is about 30, this is about 250, this is a lot. No, this is a lot, this is the lot. Okay, when the variables have very, very different scales, in general, it's complicated to move around, because you can take steps as large as the smallest components allows you. Generally, you can compensate for that by rescaling your proposal, and but you cannot do it in this case, because your rescaling would be a linear transformation, and you cannot apply one here because it keeps changing. So these are like 3 very good reasons why this distribution is very, very, very difficult to sample from. And this is one of the many, many shapes that you can get from the hybrid Rosnberg distribution. And also, you're not limited to that, essentially. I mean, you can get stuff like this, like if you use a sinusoidal like mean function, and then if you compound it with an exponential, you can get stuff that is, curved and multimodal at the same time, which is quite pretty to look at, in my opinion. And then you can also use, for example, a logistic function as the mean function, and then you can get curve distributions here that are not actually multimodal. But then you have so many, there are so many possibilities to of shapes that you can get. Really, it's a very, very flexible model, and you can use it to assess convergence of your own algorithm as well. I used it for like testing new MCMC algorithms, but it can be used to assess convergence as well. And if you think about it, the pros of this hybrid Rosnberg benchmark model is that it's very, very flexible. You can pretty much get any shape you want. The normalization constant is known, which makes it very, very easy to test how well you're doing. It can be made arbitrarily easier or more difficult. No problem, just tweaking the parameters. We know exactly what they do. And one good thing is that if you increase the dimension of the state space, this model doesn't really break because we know exactly what it looks like, which is something that often happens, like I mentioned, with other models. You maintain the features because of which you chose this model. And maybe the coolest thing is that because they are basically all normal distributions in a sense, it's very easy to draw a completely independent Monte Carlo sample. So whenever some analytical result is not quite available for this model, you can just draw a sample, a stupidly large sample, and approximate it with very, very good precision. So it's very, very flexible. One of the possible cons, I couldn't really think any of them, but one of the possible cons is that some people don't really have the time to think about this side of the analysis they're doing very much. So, and using this makes you think about what you're doing and why. So this could be a possible cons for them, but you know. And then I thought, I'm claiming that this is a very flexible model, right? And then I thought, let's try to do that, to shape it as the posterior that my colleague got from his model. And this is what I got with like 15 minutes of work. If you remember, the shape of the posterior was the following. So you had like two banana distributions. Then you had like, let's ignore the multiple modes for a second. You have a bunch of reasonably round posteriors around here. You have like a ridge here, two bananas, and the rest is not super important. So that's what I kept in mind when I shaped it. And we've got a V, we got two Vs, even though not exactly in the same place. We've got like round things down here and something that looks a bit like a ridge here. These distributions are V-like, not really L-like. I know. In principle, though, it's not a problem because if you're doing Metropolis Hastings, like my colleague is, then you're going to use a rotation matrix. So instead of rotating the distribution, you're going to just rotate the proposal, and they are essentially equivalent. So that's why the V's instead of L's don't matter in that case. And yeah, this is what I got playing with it for like 15 minutes. So it's not that hard. And this is before I learned how to do L shapes like this one. But anyway, yeah, there's hours of fun to be had here. Like I said, curve distributions, you can ignore them if you want to, but you shouldn't because things can go really, really wrong, and sometimes it's hard to detect it. Okay. For example, I've been asked to show this kind of plot. This is a random walk Metropolis run. Okay, admittedly, it's just 1 million, but then in the next plot, I'll show you that if you increase it a lot, it doesn't really make a difference. It's just 1 million samples from this model, this hybrid Rosnberg. So this is what the model looks like. And this is what you see after 1 million random walk samples, right? It's not even close to what it should be, right? If you look at the scales here, which I realize they're a little bit small, this goes from -2 to 2. So instead of having a range of 30, it has a range of 4. This goes from like 0 to 4. So it has a range of 4 instead of 250. And this went up to 10 to the power 4, almost 11 to the power, almost 10 to the power 5. And this goes up to 4. So like, if you look at the scales, It's not even close to what it should be. I mean, you get the gist of the shape, which is important. And then, once you observe this, you should think, okay, these are curved shapes. I should probably run a smarter algorithm than the random walk metropolis. This is your warning sign, okay? Here it got stuck, obviously. There's so many problems. But yeah, this is what I mean. Once you run an algorithm for a preliminary run and then you realize that the shapes are curved, then you should like stop and do a bunch of tests and especially move on to a better algorithm if you can. To do this in a slightly more principled way, I plotted the okay, great. I plotted the QQ plots for the same model, but this time I compared, instead of 1 million random walk samples, I compared 100 million of them versus 1 million samples from a simplified manifold Mala. Also, I took 100 million samples for HMC, tuned in a naive way. Okay, so not really. Hey, bear in mind that HMC in this case is like 20 times more expensive than random walk. Okay, so here the 95% confidence intervals, I think they're more or less here. I forgot to plot them. And as you can see, the black line representing 1 million samples from Mala is fairly close to what it should be. So no worries there. This is a reliable algorithm, right? What worries me is that the random walk metropolis, the red line, is very, very far from the quantized that we should be observing, as you've seen in the previous plot. And this is not even for 1 million samples. This is for 100 million samples. So when you run things on curve distributions, telling yourself, oh, I'll just run it for 10 times as many samples and everything will be fine. That's not necessarily true. It depends on how difficult your model is, okay? And doing those tests and testing your algorithm on benchmark models can help you spot the fact that you're not doing as well as you should be doing. Interestingly, tuning HMC by maximizing the effective sample size per second, which sounds sensible in theory, doesn't really work well. And as you can see, even though HMC is 20 times more expensive per iteration than random walk metropolis, you don't really get that much further. You don't really get near the 95% confidence interval mark of the distribution. You basically never get into the tails and you never explore them. So the tail uncertainty will never be represented, not even vaguely properly here. And this is just for the first component. Similar stories happen for the other components. As you can see, the random walk is super far from, it doesn't even get close to the tails of the distribution. So this is what can happen. And this is despite the huge number of samples that I took. So this is why I'm saying just be careful. And this example was not balanced for computational effort. These results are, and because of, I basically run these algorithms on my benchmark model where I know the ground truth. And because of that, because of that, I can tell you exactly how much better an algorithm is than other algorithms in that case. And so this slide is a bit dense. I've tested 4 algorithms, right? HMC tuned in the naive way I explained before, maximizing the effective sample size per second. Simplified manifold Mala, which is an algorithm that is basically Mala with that is smarter in the sense that the proposal of the algorithm is adapted with the local Hessian of the target. So if the target is flat, you're going to take larger steps. If the target is very, very peaked, you're going to take smaller steps. So it's a smart algorithm. Random walk metropolis, as usual, the usual thing. And nuts from Stan, which is a smart HMC, almost completely adaptive. These are the 4 algorithms I tested. What did I measure for them? I tested them on the model, on the 5-dimensional model that I showed you before, this one. And I measured the Kolmogorov-Smirnov distance and the Anderson-Darling distance on the marginals, and not all of them. I just took the worst distance amongst all marginal distances. Also note that everything is in log scale, so one notch up is one order of magnitude up, and the B parameter basically is this is a variance parameter from the distribution, and it basically gives you a sense of how difficult to sample from the distribution. So a low parameter means that it's easy, while a high value of the parameter, it means that it's harder to sample from the distribution, just because instead of being fatter and wider, it's much narrower. Basically, that's the reason why. And it's harder to sort of jump from one arm of the distribution to the other and that sort of thing. So, okay. What is the Kolmogorov-Smirnov distance? The Kolmogorov-Smirnov distance is a distance on the CDF of the sample that you are taking, and it's defined as the sup of the absolute value of the CDF from your MCMC sample minus the value of the CDF from the truth through CDF. Okay, this is how it's defined, and because of this definition, why they measure two of them, right? Because the Kolmogorov-Smirnov distance is defined in this way, because the sup, generally the sup tends to fall, if I'm plotting like PDFs instead of CDFs, right? Measuring the sup, we're measuring the supremum, right? And the supremum tends to fall where there's more room to disagree between the two distributions, which is normally around the mode. Okay, while the tails are already quite low, so there isn't much room for disagreement. And this is why the supremum, the Kolmogorov-Smirnov distance tends to pick up more stuff that more like discrepancies that happen around the mode rather than in the tails of distribution. This is its weakness, and this is why I also measure the Anderson-Darling distance, which is a kind of a slightly different distance on the CDF of a distribution, which gives a lot more weight to what happens in the tails. So whenever what the Kolmogorov distance doesn't get to sort of detect, usually the Anderson-Darling distance does get. And this is why I measured two of them. And interestingly, they seem to agree quite a lot in general. So this is very encouraging for the robustness of this result. Let's get to the plots now. The simplified manifold mala is like the algorithm I trust for these kind of things, and it sort of provides me with a thermal comparison of how well things are going. And as you can see, when I decided that when I said that the distribution would be easier to sample from, then the simplified manifold mala has a smaller distance from the truth, which is exactly the behavior I would expect. Interestingly, if you look at the green triangle, which represents the random walk, it doesn't really get much better, even when the distribution gets easier. And that is because it basically never leaves the mode and it doesn't really explore the distribution anyway. So this is food for thought, right? So when if the distribution is very, very difficult, then the random walk metropolis is not a good algorithm for it, despite the huge number of samples you may take. Another interesting thing is that tuning HMC naively, maximizing the effective sample size per second, doesn't work really well, very well at all, because the algorithm basically, the dynamics basically is reduced to something more diffusive than it should be, and its performance is not that much better than the random walk metropolis itself, if you tune it that way, especially around the mode. It does go and explore the tails a little bit better, like we saw from the QQ plots, but in the end, it's not quite good enough. The simplified manifold mala, we've seen it already, but the true surprise is NUTS for me here, because NUTS is an algorithm that works because it works by using a global conditioning matrix, a bit like the random walk would do. So I did not expect it to be exceedingly good on this example, because there is no global conditioning matrix that can describe appropriately all the areas of the distribution, because it changes, right? And yeah, despite that, NUTS is actually quite good, because NUTS is very good at exploring ridges, and because it's so adaptive, it can stop the trajectory whenever it's appropriate. And because of the property, essentially, it also works very, very well on curved ridges. And you can see that its performance is basically as good or marginally better than simplified manifold Mala, which is an algorithm made for this kind of distribution, even though it only takes one step per iteration. And surprisingly, it explores the tails actually much better than the simplified manifold Mala, just because of its coherent exploration according to the Hamiltonian dynamics, right? Which was very surprising and very interesting. So if you can use STEN and use NUTS, that's probably one of the easy things to do. So yeah, this is a cool result that we have in the paper that we published recently. So in summary, if you encounter posterior distributions, I would, well, just talk to me. I don't mind chatting about these things. Actually, it's quite fun. Well, that's probably the easiest thing you can do. Another thing you can do is see some simple transformations like this one, turns your curved posterior into a straight ridge, which sometimes they do work, especially in epidemiology, where the problems happen with like rates, which are positive quantities. Yeah. So that's another thing you can do. Yet another thing you can do is you can divide the components of your posterior into like non-problematic ones and problematic ones. And for the easy ones, you can do normal random walk metropolis, while for the problematic ones, you can do a simplified manifold Mala, just on those to sort of reduce the computational burden of the algorithm. And this is doable also because you can take my simplified manifold Mala code from GitHub, and I don't mind. Another thing you can do is you can take the hybrid Rosnberg, shape it as a slightly more extreme version of your target, because about your target, you only see what you've seen, you don't know what you haven't seen yet. So you've got to be conservative and shape it in a slightly more extreme version. And see, and then you can run your current algorithm and see whether the result is more or less close to what you expected or not. If it's not, then you know you have a problem for sure. And in that case, I can help, obviously, if you want to get in touch. Also shaping the distribution. Another thing you can do, obviously, is you can look into statistical tests and pick some tests to run on your MCMC sample. That is a very sensible thing to do, but just be careful to what exactly the test does and measures. So there are some tests that compare the first half of the chain to the second half of the chain, for example. And if your random walk is stuck around the mode of the distribution, it may very well be that this test says, great, you've converged, when in truth, you've really not. So just be careful to the assumptions, okay? And as a final remark, you should really be using multiple tools to get to the same result, because in case something goes wrong, you have a different tool to rely on. Okay, and if they all agree with each other, then that is a sign of robustness of your conclusion. Okay, and yeah, so I guess that was it. Thank you for your attention.